at sequence and series. Already I did some explanations about the introduction to sequence and series, like in the last class on the Google Classroom. Unfortunately, we couldn't record that class, so I will briefly go over the lesson on sequence and series, the introduction. So briefly, we are going to look at what sequences are and how do you identify a sequence, how do you recognize that a sequence is existing or not. Then we will look at arithmetic progression. So that's the objective for today. We will look at sequences, and then later we'll be looking at arithmetic sequences. Now, when you have a list of numbers, 2, 4, 6, 8, 10, etc., this is not just randomly arranging numbers. These numbers, if you look at it carefully, there is a rule that is connecting them. Like this is the first number here, 2. The next one, you are 2. The next one, you are 2. This one also, you are 2. You are 2. So you can see there is a relationship between these numbers. Now when there exists a relationship between numbers, eventually what you have is a sequence. It's a line of numbers that follow a defined rule, meaning there must be a rule that connects them. There must be a rule that relates them. Now, I can give you another example. When you have this number 1, 2, 4, 7, 11, etc. Now you may think this is just arranging numbers randomly again, but eventually if you look right into it, you will see that there is a relationship that is still connecting them. Here between this number 1 and 2, you have only a difference of 1. Between 2 and 4, you have a difference of 2. Between 4 and 7, you have a difference of 3. Between 7 and 11, you have a difference of 4. So this will continue. The next difference should be 5. If you add 5 to 11, that should give you 16. So the next difference is 6. So because there is a rule that is connecting them, this is also a sequence. Now if you look at the following numbers, 1, 4, 9, 16, 25, 36, and so on. What you have here is numbers that are square. Essentially, if you relate this line of numbers, what you can have is this is 1 square. That's 1 times 1, and that gives you 1. The next one is 2 square. 2 times 2 gives you 4. The next one is 3 square. 3 times 3 gives you 9. Next one is 4 square. 4 times 4 gives you 16. The next one is 5 square. 5 times 5 gives you 25. Next to that you have 6 square. 6 square gives you 36. So this sequence is referring to the square numbers. Now the square numbers also have another name, which is called perfect squares. So one difference you can realize, sometimes the difference is the same, that's constant difference. Sometimes you have a relationship that is different. This is an increasing order. You have 1, 2, 3, 4, 5, so it's an increasing order. Sometimes you have an exponential relationship, and this is an exponential relationship because what you do to get this line of numbers is you square the natural numbers. When you square the natural numbers, this is what you get. Now sequences looks into patterns. Sequences looks into patterns. So it could be numbers, it could be patterns, it could be objects, it could be something else. but there must be a relationship that is connecting what you are referring to. So, and these patterns must be recognizable. So when a set has a specific pattern, or other it can be further described, then that particular object or that particular thing or that particular number or those numbers are referred to as a sequence. That gives you a sequence, right? But there must be something that is connecting the objects, or there must be something that is connecting the numbers, there must be something that is connecting the things. So whichever things or numbers or objects that we are talking about, there must be a relationship. Let's look at this diagram. Now, there is some description about some squares that are touching all the sides. For example, if you have a square and a circle inscribed, and for the circle to touch all the four corners, it means then it has to be 1. So if you want to increase the square, for you to have all the circles that will touch, that it means you have to add 3 circles to the first one. It means from the first one to the second one, you must add 3 circles. Now, if you want to increase it to the third one, you must add 5 circles. That is what you are seeing here. And that's the relationship going here. So this is giving you a sequence because the output is giving you some kind of relationship that can help you to further describe this shape. Now, if you put everything together, this is what you have. Now, if I should ask you to pause and write me what is going to be the next square, how many circles will you have in the next square? That means if you have to add another square here, how many circles will you add inside there? So if you know the relationship here, you can continue, because you see this is 1, the next one is 4, the next one is 9, next one is 16, next one is 25, the next one will be 36. Because I have already seen the pattern. This pattern is giving you the square numbers, which we just discussed previously, the square numbers. Or you can call them perfect squares. Now, a perfect square is when you multiply 2 the same numbers, the answer that you have. 1 times 1 gives you 1. 1 is a perfect square. 2 times 2 gives you 4. 2 is not a perfect square, but 4 is a perfect square. 3 times 3 is 9. 3 is not a perfect square, but 9 is. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 64, 81, 100, 121, 144, 169, 196, 225, and so on. Those are perfect squares. When you multiply 2 the same numbers, 20 times 20 is 400. 400 is a perfect square. So the first 5 perfect squares that we have is 1, 4, 9, 16, and 25. Those are the first 5 perfect squares. So let's look at some vocabulary. Now, like I said, a sequence is a line of numbers that follows a defined rule. It's a list of numbers that follow a defined rule. So for a sequence to exist, these objects or these numbers must have a rule that is connecting them. For example, if you have a deck of playing cards, you have the hearts, you have the joker, you have, so in a deck of playing cards, there are always 52 cards. 52 cards. So if I ask you how many hearts are there, you can tell me how many hearts are there, because that is corresponding to that relationship. So you also have these types of numbers here. what you have is 1, 3, 5, 7. If you look at it carefully, you recognize them as odd numbers. Now, odd numbers are numbers that if you divide by 2, you have a remainder of 1. For example, 3 divided by 2, there is only one group of 2 in 3, the remainder is 1. Anytime you divide them by 2, there comes a remainder of 1. So 1, 3, 5, 7 is an example of a sequence. 1, 3, 5, 7 is an example of a sequence. What made it a sequence is because there is a relationship between these numbers. What is the relationship? So if you write 1, what will you do to get 3? You add 2. That gives you 3. What will you do to get 5? You add 2 to 3. That gives you 5. What will you do to get 7? Add 2, 5. That will give you 7. What will you do to get the next number? Just add 2 to 7. That will give you the next number, which is 9. And you can always continue because the rule is there. You've seen the rule. So once there exists a rule, it is a sequence. Similarly, you also have the even numbers. If a number is not odd, it's even. These two are opposites. If you look at the natural number sets, it's just like in human. If you are not a man, you are a woman. Of course, we have people now who are not men, not women. But obviously, this is existing. With numbers, there must be two things. You can either be odd or even. So if one is odd, then the next number is even. And that's how they are lying next to each other. If you count the natural numbers, the first one is odd, the second one is even. The third one is odd, the fourth one is even. The fifth one is odd, the next one is even. So those are opposites. So an even number is the numbers that if you divide by 2, exactly, you have no remainder, meaning the remainder becomes 0. So 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, etc. This list is the list of even numbers. So that's also a sequence because there is a common difference of 2. You have the square numbers, which we already discussed, 1, 4, 9, 16, 25, 36. That is also a sequence. You have the polygons. Now, the first polygon you have is a triangle. A triangle is 3 sides. The next one you have is a quadrilateral. A quadrilateral is 4 sides. The next one you see in the diagram is a pentagon. A pentagon is 5 sides. Next you have a hexagon, which is 6 sides. Then if I have to continue this list, you will have the 7-sided polygon, which is a heptagon. You also have the 8-sided polygon, which is an octagon. You have a 9-sided polygon, which is a nonagon. You have a 10-sided polygon, which is a decagon. So, and the list continues. Once you can continue the list, because there is a relationship, and that is why you can continue. And that relationship is what defines it as a sequence. It's what makes it a sequence. So whether it is about object, whether it is about numbers, or whether it is about some playing cards or something else, there must be a relationship that connects them. One thing I want to emphasize from this point is looking at the sequence. Looking at the sequence itself. Let me try to clean up a bit. Now, if you look at this sequence, in this case we said this is the first term, and anytime you have a sequence defined, the first object or the first number or the first thing is always referred to as the first term. So 1 is the first term, which is represented with A. We will learn that later from when we go to the types of sequences. Then this term is going to be the second term. 3, 5 will be the third term. 7 will be the fourth term. Then the fifth term will be 9. If I ask you what is going to be the sixth term of this sequence, the sixth term is 11. What is going to be the fifth term? The fifth term is 9. So exactly, so you know that they are positioned according to how they come. Now, if a sequence has 3 dots at the end, that says that sequence does not end. It continues to infinity. It means this sequence has no last term. This is the first term, This is the second term. This is the third term. That's the fourth term. But it's not the last term. Huh? The last term is not there because this is not finishing. There is no ending for this sequence. If it was just 1, 3, 5, 7, for example, 1, 3, 5, 7, only this sequence is just made up with 4 terms. This is a sequence that is made up with 4 terms. Why 4 terms? Because the last term here is 7. The last term is 7. That was what I just explained. And that's giving you some notations to use when it comes to writing the first term. If a sequence is referred to as AN, for example, that is, the sequence is named AN. So the first term will be A1. The second term will be A2. The third term will be A3. The fourth term will be A4, and this continues. So AN here, N represents the number of terms. So the first term will come as 1, the second term will come as 2, the third term will come as 3, the fourth term will come as 4. So in that case, the first term is 1, the second term is 3, the third term is 5, the fourth term is 7. The fourth term is 7. So that continues on the notations, which you can always read on the PowerPoint. It can explain more about how you denote sequences. We look at this specific type of sequence here, which we already talked about, is the sequence on polygons. And that will be the last part of this first video that I am explaining. So find the rule for the sequence of the numbers of diagonals in a regular polygon, then state the domain and the range. I want to talk to you about what is the domain and what is a range. But before going there, first we need to identify what a diagonal is. If you have a square, for example, let's say this is not drawn to scale, it's my square. Now if I want to divide this square, I can divide it this way, that is vertically. I can divide it this way, horizontally. But also, I can divide the square diagonally. So the line that is slanting is referred to as a diagonal. So if I should ask, how many diagonals does a square have? A square has only 2 diagonals. Alright? So if you look at the shapes here, now look at it carefully. The shape here is a triangle. It has 3 sides. This shape here has 4 sides. This shape here has 5 sides. This has 6 sides. Sides in as boundaries. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. That's what I mean. The outside boundaries is what is referred to as the sides. Now, the diagonals is the lines that is slanting opposing angles, at opposing angles. So if you look at it here, no, it's not what I want. Sorry. Yeah. The diagonals, I'm bringing a different color for the diagonal. Okay, let's count. 1, 2, 3, 4, 5. So you could see that the pentagon has 5 diagonals. It has 5 diagonals. So the hexagon has 9 diagonals. So the square has 2 diagonals and the triangle has 0 diagonals. So there are 2 sequences here. 1, a sequence in relation to this number of sides, and 2, a sequence in relation to the number of diagonals. So that's where I'm going to stop for now.